For years, the artificial intelligence industry has operated under a strict mathematical consensus known as the chinchilla scaling laws, established by DeepMind to dictate exactly how to build an optimal large language model. The core rule dictates a ratio. For every single parameter in a neural network, you must train the model on roughly 20 tokens of data. This specific geometry minimizes the massive computational cost required during the initial training phase. This chart plots pre-training loss against computational flops. To define an efficient architecture, developers look for the precise intersection where adding parameters and adding training data become equally expensive paths to lowering the loss. This mathematical optimization relies entirely on an assumption that is no longer true. It assumes the cost of running the model after it is trained, the inference phase, is zero. The industry is transitioning into the era of agentic AI. Instead of generating a single text response to a human prompt, these autonomous models execute continuous, multi-step reasoning loops to solve complex logic problems on their own. Generating continuous loops requires hardware. As an agent works autonomously in the background, the compute required to serve those constant inference requests rapidly eclipses the initial cost of training the network. These abstract equations must run on physical silicon. Processing trillions of tokens pulls massive electricity through finite hardware, exposing the limits of data center capacity. To make autonomous agents economically viable, developers must recalculate the scaling laws to optimize for a model's total lifecycle, integrating the exact physical constraints of next-generation server hardware. Calculating this lifecycle requires isolating the exact hardware operations a standard transformer architecture executes. The established approximation is direct. A model performs 6 operations per parameter for every token it processes during training, but only 2 operations per parameter for every token it generates during inference. The new mathematical objective optimizes for both. Developers must minimize the sum of training operations and lifetime inference operations, while strictly holding the pre-training loss target constant. Adding a variable for total lifetime inference tokens forces the optimal model geometry to shift entirely. This contour plot maps optimal model size. As inference demand scales, optimal parameter count drops sharply. To offset this, the model must absorb exponentially more information. This second chart demonstrates the exact inverse reaction. Optimal pre-training tokens expand outward. We can apply these modified equations to a practical deployment, projecting 10 trillion lifetime inference tokens. Under that load, deploying a standard 30 billion parameter architecture is inefficient. The total lifecycle compute is vastly reduced by building a smaller 13.6 billion parameter model and training it on nearly 3 times the baseline data. You accept a massive computational penalty up front during the training phase. By deploying a heavily compressed architecture, you permanently reduce the compounding hardware tax incurred during continuous inference. This strategy operates on a pure algorithmic theory that has historically faced heavy academic pushback regarding network capacity. The prevailing assumption is that tightly constrained parameter counts face a strict saturation limit. The theory posits that once a small model processes a certain volume of data, it simply lacks the internal architecture to extract any further utility. To test this hypothesized limit, researchers engineered an experimental sweep, fully training 47 individual models across a precise grid of sizes and data volumes. This graph maps pre-training loss against the ratio of tokens to parameters. Following the dark blue line representing a 150 million parameter model reveals the reality. Even pushed to an extreme ratio of 10,000 tokens per parameter, the loss descends linearly. The architecture never saturates. Pre-training loss is an abstract metric. A decreasing loss curve only matters if the network translates that efficiency into actual logic and reasoning tasks. This specific chart measures downstream performance across evaluation benchmarks.
The lines track upward. Extending the token ratios directly yields measurable, sustained improvements in reasoning capability. The original DeepMind equations failed to predict this sustained scaling because of a severe bias in their foundational curve fitting. The empirical data used to construct the initial chinchilla formula was restricted, drawn almost entirely from training runs capped below 100 tokens per parameter. This plot pinpoints the mathematical divergence. Look at the gap between the dotted curve predicting performance and the solid empirical data points recorded at extreme scales. Developing equations solely from typical ratios severely overestimates the difficulty of training small models for extended durations. The empirical results confirm that extreme overtraining works. Condensing knowledge into highly constrained architectures provides the exact geometry required to execute continuous agentic inference economically. Defining the optimal algorithmic geometry only solves the software variable. Executing it requires confronting the physical economics of the data center. Theoretical flops do not determine the financial cost of a model. That is governed by model flops utilization, or MFU, the exact percentage of a GPU's theoretical maximum compute that it actually achieves during operation. Training pipelines are highly optimized. Data is processed in massive parallel batches, keeping the silicon fully utilized. Inference generation operates sequentially, generating one token at a time, leaving compute cores waiting idle for data to cross the memory bandwidth. Training routines consistently operate at roughly 50% MFU. When that exact same architecture switches to generating output tokens, utilization collapses to a severe 1%. Breaking this memory bandwidth bottleneck requires specialized physical infrastructure. This is the engineering objective defining NVIDIA's Blackwell architecture. Blackwell attacks the inefficiency through silicon density. The second-generation transformer engine processes native 4-bit floating point precision, physically doubling compute capacity and allowable model sizes directly on the chip. The architecture accelerates data movement between GPUs. The fifth-generation NVLink unifies 576 processors, driving interconnect throughput to 1.8 terabytes per second. These physical hardware specifications alter the algorithmic math. They drastically reduce the per-flop cost of calculation and raise output utilization, lowering the financial break-even point for continuous reasoning. Software strategy is entirely downstream of hardware constraints. Blackwell's engineered efficiency provides the physical substrate required to deploy continuous reasoning models at scale. The industry is officially abandoning architectures designed to ingest massive datasets solely to output shallow, single-prompt responses. Agentic deployment demands smaller, highly compressed models heavily overtrained to execute deep, multi-step internal logic checks. This maps the exact trajectory of development. Engineering focus is migrating away from massive scale, directing resources specifically into expanding reasoning depth. Pairing these compressed software geometries with highly efficient hardware eliminates the need to aggressively strip away a model's cognitive capabilities to achieve acceptable latency. This strategy introduces an immediate input constraint. To hit these extreme token-to-parameter ratios, developers are rapidly exhausting the global supply of high-quality human text available for pre-training. The second constraint is strictly physical, heat. Running continuous inference loops on these dense clusters requires extreme power, pushing specific server racks to draw 120 kilowatts. Dissipating that density has forced data centers to abandon traditional air conditioning, requiring massive structural overhauls to pump chilled water directly to the server racks. The baseline cost of calculation is collapsing. Moving forward, competitive advantage is no longer determined by the size of the neural network. It relies entirely on acquiring proprietary training data and engineering the massive liquid cooling infrastructure required to keep the silicon operational.